Now that you've had a little bit of experience using proof by induction, we're going to formalize the process of doing a proof by induction. So we're going to describe what the actual steps are in a proof by induction. We're going to provide a model so that you can see why the proof by induction actually makes sense. Because proof by induction, looking at the steps, it's very hard to see how that gives you an actual proof sometimes. And we're going to use proof by induction on a particular problem. So first of all, I want to talk about which statements that we can actually prove by induction. And they look something like the following. For all n greater than or equal to 1, P of n, where P of n is some statement about n. So, I mean, if you think back to when we were looking at quantitative statements, what this is a universal quantitative statement, in other words, a for all statement, where the domain of discourse is natural numbers. Right, so we're looking at natural numbers here greater than or equal to 1, but we could look at other types of theorems where n is greater than or equal to 0, or n is greater than or equal to some other type of number. So for an example is, if for all n greater than or equal to 1, if we add up all the odd numbers between 1 and 2n minus 1, we get n squared. So that equation on the very last part, that's our P of n. That's our statement about n. It's an equation. If you plug in a value of n, it would give you a statement. So here are the steps we use in proof by induction. We have two main steps. The first is what's called the base case. And that just means prove the first case. Prove the theorem for n equals 1. That's a little bit like when we were doing recursively defined statements, where we defined explicitly what the first term was. So in other words, we prove P of 1. So in the example, what you do is you go up to n minus 1 on the left-hand side of the equation. That means you're adding up all the numbers between 1 and 2 times 1 minus 1. So between 1 and 1, that's just 1. And then that should be equal to n squared, which is 1 squared. And yeah, 1 is equal to 1 squared. Base case is done. For the inductive step, what you do is you basically show how to get from the step n equals k to the step n equals k plus 1. What that means procedurally is you assume the theorem is true for n equals k and prove the theorem is true for n equals k plus 1. So in the example, what you do is you assume that when you add up all the numbers between the odd numbers between 1 and 2k minus 1, you get k squared. And then you show that when you add up all the odd numbers between 1 and 2 times k plus 1 minus 1, you get k plus 1 squared. So a major question you might ask is, why does that even logically sound? Well, there's a couple ways you can think of it. In the previous video, I kind of thought of it in terms of recursively defined sequence. I'm going to give you another way of thinking about it where it's more of a programming perspective. Think of it as a Python function, or at least think of the inductive step part of it as the Python function. So what the function is going to do is its input is going to be some theorem about n equals k, the theorem about n equals k, and the output is going to be the theorem about n equals k plus 1. And what the function actually does, it assumes that n equals k case is true and shows you through logical steps why it is that n equals k plus 1 case is also true. So then what we do was we prove once we have that function that tells us, okay, as long as the n equals k case is true, I can prove that the n equals k plus 1 case is true. Then you prove the n equals 1 case independently and then put that into the function. Now that n equals 1 case is a true case. The function tells you how to get from n equals 1, now our k equals 1, from the n equals 1 case to the n equals 2 case. That will prove that the n equals 2 case is true. Now, once we've proven that the n equals 2 case is true, we can feed that right back into our function. Since the n equals 2 case is true, then the function will tell us why the n equals 3 case is true. And then, now that we know that n equals 3 case is true, we put that into the function that tells us why the n equals 4 case is true. And we just keep on going. Each time the program runs, we take a case that we just proved and put that into the function, and it proves the next case for us. So if we let this function continue to run, it will prove every single case in this way. So that means if we want to prove a statement that's appropriate for proof by induction, we only need to do two things. We need to prove the n equals 1 case, that's our base case. And then we have to sort of create our Python function. But in this case, the Python function is going to be a sequence of logical steps that tells us how to get from the n equals k case to the n equals k plus 1 case. And that is our inductive step. So if I want to prove that 1 plus 3, the sum of all the odd numbers between 1 and 2n minus 1 is equal to n squared, of course I do the n equals 1 case. That means on the left-hand side, I've got to stop at 1, so I just get plain old 1. On the right-hand side, we get 1 squared. I just have to prove that 1 is equal to 1 squared, and that is easy, right? 1 squared equals 1 is obvious to show. Now, the inductive step is a little bit abstract, so sometimes it helps to do a couple concrete practice rounds. So instead of saying, okay, let's start at the n equals k case and show how to get to the n equals k plus 1 case, well, I just proved the n equals 1 case. Why don't I show how to get from the n equals 1 case, where I'm assuming that 1 is equal to 1 squared, and then show how to get to the n equals 2 case, that is 1 plus 3 equals 2 squared. Okay? And I want to do it in a way that I can eventually do in the general case, which means I don't want to be too smarty pants about it. I don't want to just say, yeah, 1 plus 3 is equal to 4, and 2 squared is also equal to 4, so they're equal. I want to do this in a way that I could do with the variables. So here's how I'm going to do it. I'm going to take that 2 squared, and I'm going to think, well, what's the relationship between 1 and 2? Well, 2 is just 1 more than 1. So maybe if I were to split that 2 on the bottom into 1 plus 1, that might make it something that I can do in general. Now, if I have 1 plus 1 squared, one thing that I can do is I can do some foiling. If I do foiling, what do? I square the first one, square the second one, multiply the two together, the 1 and the 1 together, and then double that, right? So I square the 1, I multiply the 1 and 1 together and double that to get 2, and then I square the 1 again. So now if I want to do 1 plus 3, how am I going to think of that one? Well, I've almost actually got exactly what I've got in the line above, right? That 1 is like 1 squared. And the 3, well, the 3 is just 1 more than 2. So I can split up that 3 into 2 plus 1. Each of those 1s is equal to 1 squared. That means I get 1 squared plus 2 plus 1 squared. But in the line above, I proved that was equal to 2 squared. So I proved that 1 plus 3 equals 2 squared. Let's do a couple more practice rounds just so we can see how this process is going to go. So now that I've just proved that 1 plus 3 equals 2 squared, that's what I get to assume. And now I want to show that 1 plus 3 plus 5 is equal to 3 squared. All right, so what's going on here? Well, if I look at that 1 plus 3 plus 5, so first of all, I'm going to look at that 3 squared just the same way I did before, right? 3 is 1 more than 2. So I'm going to split that 3 into 2 plus 1. I'm going to do some foiling on it, which means I square the 2. I multiply 2 times 1 and double it to get 4. And then I square the 1 to get 1. Now let's see what I'm going to do with that 1 plus 3 plus 5. If I look at the very top row, I get to assume, remember, that 1 plus 3 equals 2 squared. And I just happen to have a 1 plus 3 and that 1 plus 3 plus 5. So if I split off that 1 plus 3 from the rest of the sum, I can replace that 1 plus 3 by my assumption by 2 squared. So I get 2 squared plus 5. That 5 is 1 more than 4, so I can write that as 4 plus 1. So I've got 2 squared plus 4 plus 1. If I look in the line above, that's exactly equal to 3 squared. So I've just proven that 1 plus 3 plus 5 equals 3 squared. One more time. We just proved that 1 plus 3 plus 5 is equal to 3 squared, so we can assume it. Let's use that to show that the next sum, 1 plus 3 plus 5 plus 7, is equal to 4 squared. Well, I'm going to do the same thing. I'm going to square the 4, write that 4 as 3 plus 1. I'm going to FOIL it. Excuse me. To get 3 squared plus 6 plus 1. Then I'm going to look at my 1 plus 3 plus 5 plus 7. Split off the 1 plus 3 plus 5. I can replace that with 3 squared to get 3 squared plus 7. Split that 7 into 6 plus 1. And that's exactly what I get in the line above for 4 squared. So, see how this is going to work? Let's do this exact same process on the general case. So I'm going to assume that all the odd numbers, if I add up all the odd numbers between 1 and 2n minus 1, I get n squared. I want to show that when I add up all the odd numbers between 1 and 2 times n plus 1 minus 1, I get n plus 1 squared. So just like before, I'm gonna first concentrate on the n plus 1 squared. And notice that the n plus 1 squared, I don't have to split it into the previous number plus 1. It's already there. So I'm going to go ahead and just FOIL that just like I normally would. So I'm going to square the n. I'm going to multiply the n times the 1 and double it to get 2n. And then I'm going to square the 1 to get 1. Now, if I look at 1 plus 3, all the odd numbers added up to 2 times n plus 1 minus 1. I'm going to split off all the terms except for the very last one, group those together, and then add the last term. Now, when I add up all the odd numbers between 1 and 2n minus 1, by what I'm assuming, that's equal to n squared. And then I add in the last part, which is just 2 times n plus 1 minus 1. I'm going to distribute that 2 to get n squared plus 2n plus 2 minus 1. Very conveniently, that 2 minus 1 is equal to 1. So I end up with n squared plus 2n plus 1. Which, if I'm looking up several lines to right below the show, that's exactly equal to n plus 1 squared. So when I add up all the odd numbers between 1 and 2 times n plus 1 minus 1, I get n plus 1 squared. That's exactly what we were trying to show. That's our inductive step. In other words, our Python function, if you want to think about it that way. So the proof is complete. So now I think you're ready to work on the activities. It's called More Induction. It has some more induction proofs for you to work on.